Again, nothing covered today will be on the final. Just the survey of advanced topics for those of you who are interested in what else is there in machine learning. This is not an exhaustive survey, but just a few topics that I thought that's interesting to talk about, and then I'll give a laundry list of other topics I did not survey at the end of this lecture. So before we talk about sort of what advanced topics, let's sort of distill at a high level what we covered in this course. In this course, we covered, for the most part, basic supervised learning. When I say basic supervised learning, I just mean sort of recipes of this form. You have some supervised training data that's pre-collected. You define a model class. You define a loss function, and then you define an objective function, learning objective based on this loss function, maybe with regularization, and you figure out how to optimize it. So this is sort of, in a nutshell, probably like 60% of the class, right? We talked about some basics of unsupervised learning. If you have just the raw features, what can you do to sort of maybe do dimensionality reduction, such as the SVM, right? We talked about sequence prediction, which is instead of predicting just a single or simple y, like a binary classification or regression, we want to predict a sequence of y's given a sequence of x's, right? So this is a conditional random field. We talked a little bit about deep learning, which is, which takes the basic supervised learning setup and says, well, instead of using a linear model class, let's learn intermediate feature representation, or layers of intermediate feature representations, and then learn a linear model at the very end. And this layer of feature representations you can think of as you can train using standard gradient sets. So the only thing that's different at a high level between deep learning and the basic models that we talked about is the fact that the function class is non-linear. Okay? We talked about some relatively simple optimization algorithms for training these machine learning problems. So we talked about stochastic, so for the most part we talked about stochastic gradient descent. And we also talked worked with EM algorithms for hidden Markov models and other types of probabilistic models. And then we also covered a few other basic concepts like cross-validation, overfitting, bias variance trade-off. And so these are things that you would use in practice to try to avoid overfitting. Okay, so that's sort of, in a nutshell, at a super high level, the types of topics we talked about in this course in very great detail throughout the lectures, but sort of at a high level is what it is. Okay, so what are some other topics related to machine learning and related to machine learning? One is learning theory. So this course, for the most part, was not very theoretical. So here's one sort of concept we study in learning theory, and it's generalization bounds. So there are many concepts people study. This is just one that I picked. And this is generalization bounds. So it's a formal, rigorous characterization of overfitting. Okay? And here's just an example result that people might want to sort of obtain. They want, for some model class, let H be the model that's trained in that model class given some training set. Then people in learning theory want to be able to obtain results of the following thing. They want to be able to prove with probability at least 1 minus delta, where delta is some small constant. So if delta is, for example, 0.1, this is with probability at least 90%. If delta is 0.01, this is with probability at least 99%. So with probability at least 1 minus delta, we want the true test error, which we cannot measure, right, to be no greater than the training error, which we can measure, plus some term, right? So the test error is upper bounded by the training error plus some term, and this term shrinks with respect to the training size. So this is sort of a flavor of a result that people want to prove in learning theory. So basically what this is that as the number of training examples sampled to IID from test distribution tends towards infinity, or as it grows, then this bound becomes tight at a rate of 1 over the square root of the training size. If you want to be super confident, right, because if you set this confidence interval really small, then with some higher probability, this bound does not hold. So this is sort of a with high probability bound where the size of this upper bound grows as the probability margin decreases. So if you want this probability very confident, delta needs to be super small, but this numerator is log of 1 over delta, so this thing grows. So if delta equals 0, the numerator is infinity, for example. Right? Yeah.
What's your relation with this formula and the central limit theorem?
So the central limit theorem is about rate. This is a tail bound. So people prove this using things like Hoeffding inequalities or Zuma Hoeffding inequalities or Chernoff bounds. Right? Central limit theorem is about, in the limit, things look like a Gaussian. Right? It doesn't say anything about the tail.
it's like central limit theorem when you like estimate the tail probability, then it results in this kind of.
So when you do central limit theorem, they say the tail converges to looking like this.
Yeah.
This is in the limit. This is a finite sample guarantee. No matter what finite n, this is always a rigorous upper bound. So that's the difference. And you can prove these bounds using applications of Hefting's inequality and things like Chernoff bounds and stuff like that. Okay, so how do you make this a rigorous upper bound for some model class? Right? That's one of the questions people study in learning theory. So one concept that has been developed in learning theory is called shattering. So the definition is a set of points is shattered by some hypothesis class of models if for all possible binary labels of these points, there exists some classifier in my hypothesis class that classifies perfectly. So for example, here are sort of a sets of 3 points. And for any arbitrary sets of 3 points in two dimensions, there exists some linear classifier in 2 dimensions that can classify any set of 3 points perfectly. Right? So if my training set is, if I have a 2-dimensional feature representation, and my training set is size 3, there always exists a linear classifier that can perfectly fit the training data. Right? So in 2D, any 3 points can always be shattered by a linear model class. So this is a notion of how well you can fit it. What type? This is a notion of what type of data you can fit perfectly with some model class. Okay, what about 4 data points? Turns out in 2-dimensional feature representations, linear models cannot shatter 4 data points because there exists, this is known as the sort of the XOR problem. There exist configurations of 4 data points such that no linear model can perfectly fit this training set. Okay, so this concept is called shattering. Using the concept of shattering, people have studied, this is a very famous result, VC dimension of a hypothesis class. So the VC dimension of a hypothesis class is the most number of points that can get into shatter. So for example, if H is linear models in 2D feature space, then we know that the VC dimension of H is 3. In general, the VC dimension, what does VC stand for? Vapnik Travonicus, 2 Russians, very famous Russians. In general, the VC dimension may be sort of difficult to compute, and you may have to like upper bound it, which makes this whole thing very loose. But if you knew the VC dimension of a hypothesis class, then you can prove that if you find the best model in your model class on the training sets, then the test error, the true error that you care about, is upper bounded by the training error plus this term. And this term basically says that it shrinks as the data set grows, depends on the VC dimension, and it grows as the confidence grows. So this is an example of result, and there are more results of this flavor. And if you're interested in sort of this type of analysis, which relies heavily on probability theory and some concepts from combinatorics, this is sort of an area that may be of interest to you.
So this result is for binary classification.
That's right. So it becomes much. I don't even know if there is such a result for multi-class classification, actually. Because this is a super general result that just holds sort of universally. So for binary classification. So I don't know. So you have to define a notion of shattering. Shattering is not well defined, or it's not clear what's the best way to define. I think there's more than one way to define shattering for multi-class classification if you want to generalize, and that makes it complicated, I think. But I don't study this topic super rigorously. I don't know all the most relevant recent work in this area, but certainly for binary classifications, this is a well-studied result. Okay. Another topic is structure prediction. So we've seen one example of structure prediction in this class, and that is part of speech tagging. So structure prediction refers to any type of prediction task where you want to predict something more than just a single regression value or binary classification or something like that. So we've seen one. We've seen part of speech tagging where it's sequence to sequence. We're given a sequence of words. We want to predict a sequence of part of speech labels. So this is, in some sense, the easiest version, or the simplest version of a structured prediction problem, where the output space is all possible sequences. And let's say there are tag-tag transitions, right, between these. That's where the structure comes from. Another one is parse trees. So given a sequence of words, I want to predict the entire parse tree of that sentence. So this is a more complicated structure, right? The output space is the space of all possible parse trees of the sentence. Right? We do rankings and information retrieval. Given some query, we want to predict a ranking, which is a combinatorial object of all possible search results for this query. And so here's one way to sort of formulate this problem very generally in the linear case. This is by now it's a fairly well-studied problem, but so here's how it works. So we have some classifier that makes classifications in a structured output space. So let capital Y of X be all possible sort of outputs. So for example, if X is a sequence of words of length 5, then Y is all possible sequences of part-of-speech tags of length 5, right? And then there's some scoring function that takes any X and Y and scores how good it is, and we want to predict the Y that has maximum score. Right? We assume that F is linear, so F can be represented in this form. Okay. In this form. So there exists some feature mapping of X and Y such that it's a linear function in that feature map. And so the quote-unquote structure of the problem is encoded in the structure of the feature map. Example 1, binary classification. Turns out that you can reduce binary classification to this setting. If the output space is just plus or minus 1 for a single Y, this feature map is just Y times the feature vector, then it reduces exactly the binary classification. So this is a strict generalization of unstructured prediction problems like binary classification. Okay. Second example. First order sequences. So we've all seen this actually, right? If this feature map decomposes additively into the sum over pairwise transitions over your output space, right? Then you can solve this using Viterbi. Right? So this is something that you've seen already in your conditional random field homework. Oops. Okay, another one is I can actually express a general integer linear program using this problem. Okay. So if my joint feature map is this, if Y is a bunch of variables that I want to solve using an integer program, and then phi is some feature vector of the inputs, right? Then I can write my scoring function as my integer variables Y. So each Y is either 0 or 1. My integer variables Y transpose C, right? Where C is basically looks like this, right? My weight vector times the feature mapping of each corresponding to each variable, right? And then the classifier basically says I want to find the integer assignments of Y that satisfies this, subject to some constraints. So if you have constraints in this integer program, they can be encoded in this Y of X, and if it's convex, everything's fine. And then you can just use any integer linear program solver to solve this optimization problem. So what does this give you? Well, there are many problems in operations research that can be formulated as an integer program, such as facility location, airline scheduling, many types of complicated optimization problems, right? Where Y encodes some global assignment of the solution. And what people in operations research do is they say, well, okay, I'm going to just pick a cost, right? I'm just going to say, oh, if you get this wrong, it costs this much. And this could be a very low-level specification because there might be thousands of such Ys, right? Well, machine learning structured prediction says, well, okay, suppose instead of trying to learn this C, I'm just giving examples of what are good solutions, right? I'm just giving a training set of what are good solutions, what are good Ys. And I'm just going to learn a function W that given any input instance X predicts what the C's are, and then I solve this integer program. So I'm going to use a machine learning to predict what is the objective of this integer linear program given any input instance, and then we'll solve using integer program. So it's sort of the inverse of these optimization problems in machine learning infrastructure. Okay, so in order for this to work well, right, you need a efficient algorithm for solving this problem, no matter what the structure of the feature map is. So if this feature map is a sort of a pairwise sequence decomposition, then you can use Viterbi. If this is a parse tree decomposition, you can use what's called a CPY parser. If this is a ranking, you could use sort. And if this is structured as an integer linear program, you could use sort of your state-of-the-art integer linear programs such as cplugs for solving. Where the machine learning part comes in, so this is all prediction, right? Given a W and given this is all sort of standard algorithms and optimization. Where the machine learning part comes in is, well, okay, we want to actually learn a W such that this optimization procedure gives me the answer that I want, right? So given examples of good assignments, good solutions, I want to train a W that minimizes some loss function. If you're using, you can use what's a generalization of support vector machines called structural SVM, in which case you minimize the hinge loss with respect to your training structure training data. We've all seen conditional random fields. We've seen only the sequence version, but but conditional random fields generalizes, in which case you're minimizing the log loss. And there's also other even simpler algorithms such as the structured perceptron. And in fact, let's just go over the structured perceptron because it's actually almost a trivial extension of the perceptron learning algorithm. So recall in the perceptron learning algorithm that this is the hypothesis. So we're doing binary classification. Training data looks like this, and we just loop through the training set in an arbitrary order and consider an example. If our hypothesis, if our current model predicts correctly, then we don't make any updates to our model. If the current model predicts incorrectly, then we update. Right? This is the perceptron learning algorithm. Structured perceptron looks almost the same, right? So now H is this optimization, is the solution to some optimization problem, right? And so we take some structured example, we make a prediction. If it agrees, we don't make any updates to our model. If it doesn't agree, we update, according to the feature representation of the training example. And that's it. So this fully sort of abstracts away. So by encoding the structure of the structured prediction problem in this feature map, right? We've completely abstracted it away, and from the learning algorithm's perspective, it just looks like a linear learning problem, and the structure is just completely encoded in this feature map. Right? So this is the structure. This is the first the first discriminative learning algorithm for structure prediction. It was initially proposed for sequence prediction. Actually, it was initially proposed for hidden Markov models type models. And this is exactly what it is. And this feature mapping is basically the sum of the pairwise features of the correct label for that instance. Okay, let's talk about support vector machines. So in a conventional support vector machine, the minimization problem looks like this, right? Where you want to minimize a regularization penalty plus a slack variable, where this slack variable is an upper bound on the 0-1 loss. In fact, it's the hinge loss, right? So this is the conventional support vector machine for binary classification. Okay, so what does the structured extension of support vector machines look like? So a structural SVM has the exact same optimization problem. It looks exactly the same. The only difference is that the constraints are a little bit more complicated. So instead of looping over, instead of considering in binary classification, support vector machines have sort of two labels, +1 or -1. And so this constraint is just sort of whether or not the correct label is better than the incorrect label. In structured prediction, there are sort of many incorrect labels, not just one. So so these constraints need to be enumerated over all possible incorrect labels, at least implicitly, and then you get the exact same flavor of a constraint. So to interpret what this means, this is the score of under the current model, this is the score of the correct label in the training set. This is the score of any other label. This is the loss of that label, so like Hamming loss, for example, and this is the slack variable. So how can we interpret these constraints? So this is the only thing that's different, right? So keep in mind that if this structured feature map is for binary classification, this whole thing collapses back to binary classification SVMs. So suppose we have some incorrect y prime, right? And the score for that y prime, so this guy, is 1.25, let's say. And the score for the ground truth y is 1, right? Then in order for this constraint to be satisfied, And let's say the loss of this y prime is 0.75, right? Half of this y prime is in disagreement with y. In order for this constraint to be satisfied, the slack variable needs to be at least 0.75, which is at least 0.5. And this is something you can prove. The slack variable is always an upper bound, so this is the hinge loss over the loss of any y prime that you might predict. And again, I'm not going to go into too much of the details. This is just to give you a flavor of the type of research questions in each of these fields. So in structured prediction, the key question is how do you learn models when their prediction algorithm when their prediction is the result of an optimization procedure, right? And so you have this sort of you have this feedback loop between learning and predicting, where the predicting is now an optimization procedure rather than just a simple scoring function. And what structural SVMs do, so what structural perceptrons do is just say, make your best prediction. If it's wrong, make an update. Right? What structural SVMs say is, well, I'm going to consider every possible misprediction simultaneously, which is exponential. So this whole thing is exponential. But then you have tricks for which you can sort of not have to actually explicitly enumerate all these constraints, so the whole optimization problem is no longer exponential. So these are the types of questions people study in this area, which is how to do efficient training when at training time this function is an optimization procedure. Okay, so we talked actually sort of tangentially a lot about crowdsourcing in this lecture because of the sort of huge cost of acquiring supervised labels, right? So this is sort of a cottage industry now, largely on Amazon Mechanical Turk, which is a website that pairs human workers with annotation tasks. So this is one that I created that I put on Amazon Mechanical Turk, where I asked people to tag locations in pairs according to some tags that I predefined. So they would look at this, they would go on here, the workers would go on this Mechanical Turk, get shown my tagging annotation task, look at this attraction in pairs, and then sort of click which tags are appropriate, and then they get paid some amount of money for doing this task, right? It's sort of just a matchmaking service for annotation tasks for workers, right? And this is sort of this is super standard right now in the machine learning community and neighboring communities such as computer vision, natural language processing, and so on and so forth. This is how we collect labels for a lot of our prototyping and research tasks. Okay, one big question in this field, because this is such a big industry now within the research community and actually within the industry as well. One big question is, well, how reliable are the annotators, right? In all of our discussion in this lecture, we just assumed that the supervised labels were perfect. Right? In reality, they are not. Right? So, in some sense, if we knew what the true labels were, like somehow we if we, as a thought experiment, knew what the actual labels were, then we could judge workers on quality because we could see how often they agreed with the true labels, right? But we don't. If we knew who the good workers were, then we could create labels from their annotations, right? So this is a chicken and egg problem, right? And this is a topic of intense study. There's a subfield that studies this problem very, very intensely because it's a very, very important problem. Like the noisy annotations can lead to, so if you have a machine learning algorithm and you know that this algorithm, like decision trees, for example, is very sensitive to label noise, and you have a very noisy training set, you can learn something that's very wrong, right? If the labels are noisy. Okay, so here's just sort of one simple approach, and this is something that I just made up. So what other people do in practice is a little bit more complicated, but this gives you a flavor of sort of the types of approaches people are considering. So we're going to have a latent variable for every worker in our pool. So that's Z of M, where M indexes over workers, to know the reliability of worker M, right? Then if I have, and let's say I've collected for every training example in my training set that I want labels for, I've asked every worker to label it, just for simplicity. In practice, that obviously doesn't happen. Then the label, if I'm sort of willing to be sort of continuous, is simply the weighted average of the labels created by my annotators, weighted by the reliability of the worker. Right? If I'm not willing to be continuous, I would just threshold this to 1 or 0, depending on whether or not this weighted average is above 0.5 or below 0.5, let's say, if it's binary classification. Okay. We can also sort of, in an EM style, say, well, okay, we have this estimate of what the ground truth labels are. Let's use that to sort of figure out the reliability of every worker by looking at the disagreement, so some loss function between the label that worker provided for that example and the sort of current estimate of ground truth. And that can give us an average reliability of the worker. And then we can sort of alternate between these two steps in an EM style, right? Until we converge. And so this would give us, in some sense, a reasonably reliable estimate of the ground truth labels. There are obviously significantly more complicated versions of this. For example, different workers might have better or worse performance on different types of annotation tasks. So you might want to do, you want to learn task-specific worker reliabilities. People have studied things like if you give a worker too many tasks in a row, they get fatigued over time, right? And so you want a time-dependent reliability variable. So that it can get very complicated. But this is just sort of the simplest version of it that you might imagine. Other people, they actually have ground truth labels that they've sort of spent a lot of money making sure that it's correct. And then they called it what do they call it? They call it an Easter egg? No. I forget what it's called, but they ask workers to generate labels for instances for which they have ground truth gold standard labels, and they use that to estimate reliability. But that's very expensive, yeah.
Does Mechanical Turk rate its workers and say can you set a threshold to say I only want this reliable of worker or something like that, or? But
unfortunately, reliability is not a unidimensional metric, so there's no agreed upon.
Well, I'm wondering if they approximate, this person is a good person, a high quality versus low, kind of accelerating type thing.
There is a metric on Mechanical Turk. I don't think it's a very sort of. I don't think it will solve this problem. It's just how often the worker gives complete garbage results, basically. They just take the money and run. So many of the larger companies have internal services. So before Amazon Mechanical Turk became public, it was a private service. So they had hired workers internally, paid them more typically, and then these workers are sort of persist throughout many months or years, and then you can have a measurement of their reliability. Google has this, Microsoft has this. Every large technology company has their own sort of service that looks like Amazon Mechanical Turk, but is internal. Right. So there's different, and if you're in a large company, it's typically you have your own internal service. So when I entered at Google, they had their own rating service, and I'm not the only person submitting jobs tasks to get rated, annotated by workers. Typically, there might be hundreds or thousands of annotation tasks submitted by various people in the company, right? And this is also true in Amazon Mechanical Turk. It's just less control over it because it's sort of more of an open market. But now, if you're sort of in a private company and you're trying to manage this whole thing, you want to get the best bang for your buck, right? Because you're paying these people. So how do you do job scheduling when there's many annotation tasks that's being submitted to the same pool of tasks, right? So different tasks are harder than others. How many labels do you want to collect for each task? These are all questions that again need to be answered when you sort of scale this up in a very sort of in a job schedule type of setting. Beyond binary classification or multi-class classification, there are more structured annotation tasks. This is especially prevalent in computer vision these days. So this is one recent result where the goal of this task is to create annotations for segmentation, right? So the correct thing to do if you have, if you want a worker to spend a lot of effort, is to do a pixel by or near pixel by pixel segmentation of the object in the foreground. Needless to say, this is supremely expensive, and some people may not have the skill to do this. I don't think I can actually do this. You could just say there's a horse in this image and there's a person in this image. Or you can say, and this is something that people have been studying trade-offs of, suppose I just sort of put a point in I just sort of put a dot on where the human, on one location where the human is, and put a dot on one location where the horse is, hopefully close to where the center of mass of where each object is. Is this sufficient, right? Or let's say you trace out like a squiggly rough skeleton of the object that you want to segment out. Is this sufficient? So these are sort of, when you do structure, when you have these structured prediction problems such as segmentation, then the full annotation is also a structured label. And then the question becomes, can I get away with less, quote unquote, partial annotations relative to the full structured label? And so similar things arise in natural language processing. Okay, so now let's talk about active learning, right? So crowdsourcing, we have unlabeled data. There's me, I'm not very rich, right? And I want to collect some labeled data, and I want to, there's this image, it's unlabeled, and I want to sort of have a worker label that as, containing a mushroom, and I want to have to pay this worker money, right? And then after the label has been acquired, this example, image, label, goes into my label training set, right? And the process repeats, right? Now, in traditional sort of passive supervised learning that we've talked about in this lecture, we assume that the labeled examples are sampled IID from the test distribution, right? What that means is that I have to sample a random image from my unlabeled set and for that to be labeled, right? Now, if there's a long tail of objects, for example, there are some objects that are very rare. Let's say mushrooms are somehow very rare in my set of unlabeled objects. And then something like this might lead to, a very long time before I can get full coverage of the training set because I'm doing IID sampling, right? This is problematic if there's a long tail, let's say. There are other reasons why you might want to avoid doing passive learning too. Active learning says something else. Active learning says, given what's currently in my labeled set, I'm going to have a strategy that chooses which unlabeled example to acquire a label for, rather than sampling from this random, uniformly at random. This is active learning. And the goal is to maximize accuracy of the subsequent trained model with minimal cost, right? Because I pay at the cost every time I ask for a label. So in comparison with passive learning, right, conventional supervised learning is considered passive learning, where the data is, we're passively given the data. We don't actively collect data, right? In passive learning, the unlabeled data are sampled according to test distribution, and we choose which ones to label at random. This is extremely expensive. There's just a simple example. This is sort of the canonical example in one dimension. So this is the sort of the simplest, the cleanest example where active learning can give a huge benefit. So imagine that we just have a one-dimensional feature representation, and we just want to run a threshold function, right? So the data points can fall anywhere along this one-dimensional feature representation, and then suppose we sample. We drew some samples IID from the distribution, and we acquired their labels, and they look like this, right? Okay, then we can sort of learn that a good model should be here, right? Sort of in between at the midpoint between the boundary between positive and negative. So I'm assuming that you can do perfect classification that this model is separable, that this classification problem is separable. Okay. And then let's say the true model is here, right? So every data point beyond to the left of this true model will be labeled positive. Every data point to the right will be labeled as negative. So we get pretty close.